map singularities, a much rougher invariant. Okay, so let's begin. So what is enumerative theory of map singularities? So in its first instance, it does is a question like this. We look two smooth manifolds and a map between M and N, and the regime we are interested in is the regime where the source manifold has lower dimension. I will later denote this by little m, and then the source, then the dimension of the image manifold, whose dimension is will be denoted by little n. And of course, well, it could be just mapping all of m in a point, but the issue is, suppose I fix a homotopy class of map, at least, or I just fix a map, in other words, and the question would be whether this f could be deformed to immerse the manifold M into the manifold N. So, for example, a classical question goes back to more than 100 years, is the question whether the projective plane can be immersed into R3. So this was one of the classical questions that motivated the area. So to understand this, we developed a little language of how map singularities are viewed, and so we will actually classify points of the source manifold M with respect to maps from M to some other manifold. Okay, now I put a little, and it's really truly cheating, but I put a little sign here. I said over C. So really, in a certain sense, one could consider everything I'm talking about over the reals, but in fact, we'll basically study holomorphic maps. Passing to the complex setting is simplifies a lot of the things I'll be talking about. Okay, so how does this classification of points or singularities of M go? Well, the simplest modern way of looking at it is that if I take a point P in the source manifold M, then I make a choice now. We choose coordinates X in the source and Y in the image near FP. So these are X and Y are coordinates valid locally near P and FP, and then the function f in these coordinates will be, one could write down as n, so equality of n functions psi I, and them together I'll denote by psi, which are since I look at now the complex setup, can be thought of as power series with no constant term, since both coordinate systems are centered at the origin. Okay, so I look at it this way. Of course, I will need to eliminate this choice of coordinates, and so the way that's done is that I introduce a group, the group of the coordinate changes, and that works as follows. So basically, it's a similar kind of structure. For each xj is changed by a function delta j, which is holomorphic in the variables x1 up to xm. So it's the same thing as this. This is just basically some power series. But now to make it a group, we will say that the Jacobian of this will go from 1 to m and not n. So there are m functions delta j. And so maybe I can even, so I would like to say that j now goes from 1 to m. And so the condition is that the Jacobian, once we set xi to be 0, should be invertible. So it should be in GLM. If once you take such a thing, then under composition, this reflects change of variables, and we obtain a group, and the group acts in some obvious manner on these i's, and will actually reflect just change passing from one coordinate system to the other coordinate system. So the way I'll write this is that I will use this kind of slightly strange symbol, this thing here. So what I mean is just a set of multiples of sides. This is basically just n tuples power series with no constant term, essentially. So this is set possible sides that we here, and then there's a right the M action, and there's a left the N action on this, where we can make changes of variables on the X side and on the Y side. Okay, so we do that. So then we obtain orbits of these double groups. So it's a product of two groups, the M and the N, and they act on this basically on this vector space of holomorphic functions in variables without constant term. So as I look at these orbits, then I eliminate I eliminated the dependence on the choice coordinate system, and so these orbits are essentially what we would call the set of abstract singularities or classes of singularities, or the classification of singularities of maps. Okay, so basically the solution for the classification is to look at these orbits. Okay, so just a small remark here, that it's a little usually we're a little bit afraid of this thing that we have an infinite infinite dimensional spaces and infinite groups, but in our case it's actually not necessary. One can easily pass to the set of d-jets. So what that means on the psi level is that I just cut I divide, basically this is a ring, this is a set of holomorphic power series, and I just cut it by killing all the monomials whose total degree is greater than d. This way I obtain a finite dimensional vector space, and I think the same thing can be done with the homomorphism group with the same cutting procedure, and then what I obtain here, I can put here if I want little d's like this, d, and d, and now everything is finite dimensional. This does not simplify the situation at all, but doesn't complicate it either. So that's so you can think of this as a finite dimensional problem, what I'll be describing next. Okay, so that's the setup, and so we have basically a linear vector space, finite dimensions, and we have this linear vector space, and then we have two groups acting left and right on them, so we can look at these orbits and basically like to study this orbit structure. Now this is infinitely complicated, absolutely no chance of being able to solve it or describe it, so I will slightly simplify the situation. I will allow myself to look at not necessarily orbits, but just some kind of, so this is a vector space now. This is a vector space. These are two algebraic groups, non-reductive groups. And I'll allow to look at algebraic subsets, subvarieties, which are invariant under these groups. I will generalize. I'll call those singularities as well. Okay. So, a very nice example of such singularities is a set of contact singularities. So contact singularities are constructed the following way. So first note that from the set of these psi's, I can construct, there's a map, which I'll denote by just ALG, into the set of algebras. And this is just a local algebra of the singularity or the point. And what it does is that if you take a psi, again, a psi is just, I recall, is just this thing, is an n-tuple of our series. Once you have these psi's, then you can just look at the set of all power series and divide by the ideal, maybe I'll mark that more clearly, by the ideal of the generated by these psi I. So this way I obtain an algebra, and this algebra is an invariant, and it's easy to verify that this algebra, this quotient algebra, does not depend on the change of coordinates up to isomorphism. And so this could be, so what I can do then is that I can fix an algebra, say for example, will be for our purposes today, this will be enough. So we just fix an algebra, say the algebra AD, which is just the algebra generated by one variables of dimension D. So for example, this one, t divided by the ideal t to the d plus 1. So this is just t squared all the way up to t to the d, right? So that's this algebra. So this looks very simple, t squared. So this is a linear span now, t to the d. Okay, so we just look at this algebra, and I can then ask the following question. For each function f, I can look at the set ADF, which will be a subset of the manifold M, where this local algebra that I defined in general this way is isomorphic to this algebra AD. And this way I can actually stratify all of the manifold M according to these local algebras. So anyone can look at, for example, A0 will be just generic points where the points are points of immersion. But then, of course, the other ones, roughly A1 is going to be the singular points, and then etc. etc. Okay, so so let's see up. So maybe let's just first look at this left-hand side. So this problem of so then the problem we're interested in, so I defined as sort of a cycle which then you need to close, and this will be then an algebraic cycle inside M, or and it is the topologic something that defines will have a homological fundamental class. So just a second up here. So this ADF, this set, I will this will be often a homologically non-trivial set, and the question posed by René Thom back in the late 50s, early 60s was, I look at this ADF, I look at this fundamental class interpreted as by Poincare duality as a cohomological class in the cohomology of M. So I think of it this way. So I'll think of it as something in the cohomology of M. And of course, this cohomology, actually the degree of this cohomological class will be the Poincare dual, so the codimension of this cycle. And so what Thom and then with the refinement of Damon discovered is the following, is that in fact, there must exist a universal polynomial, which I'll denote by TH for Thom, D, which just specifies this algebra, and then there's this n minus m. So it turns out that the polynomial we are looking for doesn't depend on n and m separately, only by n minus m, only on their difference. So there's a universal polynomial and so now in what? So I write CZF, but I'll tell you what CZF is basically the difference bundle of this map, or if you could say the characteristic Chern polynomial of the map F. This is an F, which is constructed in such a way. So up you put the total Chern class of the pullback tangent bundle. So you look at F star Tn, you pull it back, and then you just look at the generating series of its Chern classes. And downstairs, similarly, you take the generating function of the Chern classes of the tangent bundle of M, and then you take the quotient and then express that in cohomology, and you call those the cohomologies, the Chern classes of the map F. Okay, so this is the Chern class. When I say it's a polynomial, and this what I mean obviously is that it's a polynomial in these Chern classes 1, C1F, C2F, etc. It's a universal polynomial on 1, C1, C2 is that whenever you have a map, you substitute into this polynomial the actual cohomology classes C1F, C2F, you get a cohomological class here, and with sufficient transversality, which I'll not specify holds, then you recover the fundamental class of the locus of the points where this algebra is a local algebra. Okay, so I don't know if there are any questions. So this was the scheme of Thom, and of course I just going back to my original setup. Of course, if you want to study this is very useful, because of course if you can prove that the fundamental class of the locus when there is some singularity is non-trivial, that means you cannot make it empty, right? So that's this topological obstruction to immersion. And so this way, using this, you can actually prove that there are no immersions for particular problems. But we'll get back to that. But for now, this is a completely reasonable way to approach this problem and find the topological obstruction. Okay, so then people started calculating these polynomials, and so the first one goes back to Portus. It's a very old result actually, and it just says, so since it only depends on the difference, for this n minus m, I introduce a new letter that's going to be L. Okay, so and then the statement is that for A1F, the answer is simply C L plus 1. So the it's called the Tom polynomial of A1 is simply CL plus 1. That's roughly, you can throw the F away. This polynomial is universal. Okay. So then the next result came, probably this is back from the 70s, Felice Ronga, who was actually, I still saw him. He was a colleague of mine here at the University of Geneva. Calculated the A2F. So the Tom polynomial for D equals 2 and arbitrary L. And so the result was this. I should have had this formula. So let's just a second. Well, doesn't matter. So the formula is a more complex. So instead of CL plus 1, you have CL plus 1 squared, and then you have CL plus 2, etc. Actually, it has this several nice properties. One is that its width, sort of the number of C's you use, is only at most 2, and the other observation, and of course the sum of coefficients is always the codimension of this cycle, so that's always 2L plus 2 in this case. That's not surprising. And so the formula goes like this. It starts with CL plus 1 squared, then you have CL plus 2, so 1 and then you have powers of 2 CL minus CL plus, then 4, the next one 8, etc., etc., etc. It goes until, of course, at some point this C will go, C0 is 1. So as you decrease this index, this is the finite formula for each particular L. So it just has L plus 1 elements. Okay, so this was the formula. And so then, well, it's a long story, but Bertzi and Szenes, this is myself, my student, Gergely Bertzi, and myself, we observed that, in fact, this, well, as I said, this is a long story, but I'll try to explain a little piece of it, can explain in this following manner. So you introduce some auxiliary variables, Z1 and Z2, and then you look at this fraction, Z1 minus Z2, 2Z1 minus Z2, and then you just multiply it by the following thing. So it's the CZF that I had here, except instead of Z, you need 1 over ZI. And it's just an artifact because we look at residues at infinity, but it's the same infinite sum. Then you shift this by ZI to the L, so in the positive direction. Well, you put DZI because it's a residue. And now by residue here, I mean an iterated residue, so it's really iterated. So what that means is that first, you think of Z1 as a constant, you take it with respect to Z2, and then you take it with respect to Z1, and also expressed by an inequality between the moduli of Z1 and Z2, Z2 being bigger. Okay, so you have this this kind of somewhat unwieldy formula where you have 2 1s at the beginning actually has a very natural interpretation like this. Okay, so this was, of course, already getting closer to the solution. And then, for example, for 3, so this formula goes back to like the 70s, and this was found already in this century, so it's 30 years later. The Tom polynomial for D equals 3 has the following form. So you take this Z1 minus Z2 and you replace it by its generalization, just a Vandermonde determinant or a Vandermonde function Z1 minus Z2, Z2 minus Z3, Z1 minus Z3. So that's what you have here. Down here, you have basically the following product. You have 2z minus z2, 2z1 minus z3, and z1 plus z2 minus z3. So you have all the linear factors where the sum of the indices of the two positive things that you have is less than equal than the last one. Okay, so I'll write this out more precisely. In general, this is the general formula. So you have, for any d, you have the Vandermonde determinant in these d variables. Then you have this standard product that you always have, C1 over zi to the L dzi. And then, as I mentioned, so you take a product of linear terms, zi plus zj minus zk, where the first sum of the first two indices is less than equal than the last index. You do that, and then you take the iterated residue in the sense that I just explained a minute ago. Okay, so this is this general formula. Now, this is not true, of course, if I don't take this red part here. Why? Is because, see, as you can see here, we were lucky a little bit. This fraction is homogeneous, and it should have homogeneous degree 0 in order for things to work out. And so that means that here, that's 2, 1, and 1. And here, the Vandermonde is 3, and there's 3 solutions. But if you look at 4, then the Vandermonde is 6-dimensional, but there are 7 solutions to I plus j less than k. So there will be something here. This is what we denote by QD. Okay. And so what did I do? Yeah. So and the correct answer for that Q, well, I'll write down what Q4 is, and Q4 had to be a linear polynomial. It's this 2z1 plus z2 minus z4. So we calculate this, and we also calculated, maybe I can write here, Q5, Q6, Q7. These are okay, but then Q8, for example, is already, well, first of all, it's an enormous polynomial, but also our computing power doesn't allow us to compute it. So this is sort of, in a certain sense, we solve the problem. In a certain sense, we don't completely understand what happens after a while. Okay, so this, I will not have time to explain how we did all this. I just want to mention the spectacular work of Maxime Kazaryan, who reinterpreted what we've done in a much cleaner and at least theoretically cleaner and clearer fashion, and has a beautiful paper on this, which is called the non-associative Hilbert scheme. So let me just say one thing about this and also just about the methods that are involved in this work. So basically so this is a reformulation, say, of Kazaryan of our interpretation of what is QD. So sorry, let me just correct this. QD. So what is QD? So QD, I say, is the equivalent Poincare dual of the following thing. So it's a clever nonlinear object, and it's the following. We look at just ordinary d-dimensional vector space. So for example, for d equals 3, it's 3, d equals 4, it's just a 4-dimensional vector space. In this calculation, what's the big advantage of it? M and N, they disappear, they play no role. So the only place where M and N appear are just these L here. See, the L is M minus N. Everything else that you see here depends only on D. So for example, D equals 3, you only have 3 variables and everything depends on that only. So the only place where you have something is this L here. Okay. So now that's having been eliminated, since this Q also doesn't depend on M and N, and so I'm describing something only depending on that. And that something is the following. So you look at this CD and you look at all kind of formal commutative but not necessarily associative products from CD to CD. And there is a very important simplifying technical issue, is that you consider this as a filtered vector space, and you consider these products only as filtration preserving product. So this is a certain 3 tensor, looks like a product. Okay, and so then inside this set, so this is a vector space, you are looking at the set of obviously associative products, and such that the resulting algebra that you get after this associative product is actually AD with its standard filtration. So remember, AD is just CT divided by TD plus 1. Okay, so this is the interpretation of QD if you know what equivariant Poincare dual is, and I'll say something about this in a second. Okay, of course, Q1, Q2, and Q3 are equal to 1, but then Q4 is equal to this thing. Okay. So I don't know if there are any questions, Chance, but if not, then I'll go. And so I'll try to explain a little bit what this is about, some things about the methods. So the methods are, so first, so there's the basic cornerstones of the theory. So this is now our view of it. And so then, as I said, Maxime is understood this in a much more elegant and manner, which also generalizes to other algebras. So the equivariant Poincare dual. So this is a certain important object that appears in many different guises. So it's called multi-degree also, and various other things. But the basic setup is the following. You take a vector space on which a torus acts with some weights, T, which is C star to the D, just a torus acts, and then you take an invariant subvariety. And to this setup, this subvariety will then have a Poincare dual. Okay, and so the Poincare dual we will denote by EPD, equivariant Poincare dual of sigma, is something in the cohomology of the equivariant cohomology of the vector space V, which is of course just since it's can be contracted to point, is just Z1 going up to, so it's just a polynomial ring in Z1 up to ZD. And then with this interpretation, one can actually interpret the Thom polynomial in the following way. So Thom polynomial, this is a D and codimension L here. It can be thought of as equivariant Poincare dual of the subset of the set of these map germs where the relevant algorithm is equal to EAD. This is a linear vector space. Action of the torus is just the rescaling of the variables x and y by just multiplying by a constant, and this is of course the condition we are interested in, where we would like to have that the map germ has local algebra equal to A. Okay, so this is simply a reinterpretation of what the Thom polynomial is, but not in a more precise manner, which via the notion of equivariant Poincare dual. And so now there is something here which I don't understand what happened here. I think there is some technical problem, but anyway, let's go. Okay, so yes, so now let me say something about so I will try to describe my work with Berzi. So this is one interpretation that we used. Next we use a variance, what I call variance cannibalistic integral formula, which looks as follows. So we write the equivariant Poincare dual of a variety sigma here as the integral of the Thom class of V over sigma. And so the equivariant Thom class of V is actually just a class in the compactly supported equivariant cohomology of V, which is actually a module over the usual equivariant cohomology of V, and it's known that it can be written this way. So that means this, as you remember, as I said, the equivariant cohomology is just a polynomial ring. And then the equivariant compactly supported equivariant cohomology is simply the same thing, but shifted up by something that has the dimension of the vector space, which is called the equivariant Thom class. And this is something completely explicit one can write. So Michel has used an explicit Gaussian version, but it can be written completely explicitly. Okay. So you get something, you get differential forms with values in the equivariant homology, and then the differential forms on V are integrated over sigma. And so the result is actually, once you integrate out the differential variables, you just have left with the Z variables, and that's what the EPD is. So finally, the important thing for us that you can calculate the equivalent Poincare dual of something by just integrating integrating a differential form, these values in polynomials over sigma, and so that's an equivalent integral. And for equivalent integrals, then there are some localization methods that one can use to calculate them. So now is a good time for me to ask how much more time do I have, because since we didn't start this and I don't remember.
You have 15 minutes.
15 minutes. Okay. Yeah. Okay. So 15 that would be basically until 2:10. Yes. So here 2:10. Okay. Something like that. Okay. Okay, thank you very much. So the steps to calculate Tom's polynomial: first, we interpret it once more as an equivalent Poincare dual, then using variance formulas to interpret this as an equivalent integral, and then use localization on singular varieties to calculate so Maxime had a slightly different view of this, but it's essentially you need some version of this. Okay. So now maybe a few more comments about these results and further development. So I didn't mention, but there's an alternative way which is also very efficient, maybe conceptually a little less transparent, but calculation sometimes even more efficient, which is Riemanni's. So let me just write it here up. Riemanni's restriction equation methods. Restriction method, which I didn't speak about, but until our result, this was maybe calculation-wise the most efficient way of calculating Tom polynomials. Then there's one thing I wanted to mention, is that there's one can also try to calculate fundamental classes in other extraordinary cohomology theories, and in particular, Riemann and myself calculated. I mean, we made progress in calculating the K-theoretical cohomology class. I mean, we only succeeded actually doing it for A2, honestly. So this is still a complicated open thing. But of course, one of the difficulties is that fundamental class in K-theory is not always clearly or uniquely defined. Actually, we found 3 different definitions, so this is kind of a complex thing. And so maybe some very recent work, I mean, there's lots of work I could mention here, but some very recent work of Riemann on the, one can extend this rather instead of Chern classes or fundamental classes, one can look at CSM classes. So one ventures into this motif theory, and so this which has been just defined, and so for now even the A0 case is not really known. So this is another direction which I think is very exciting related to homologic theory, etc. Maybe one last thing, as there's a famous Riemann conjecture, which also motivated my work, and that says that the coefficients are non-negative. So if you look at the Tom polynomials coefficients are non-negative. I mean, so this is a rather outstanding conjecture, which is related to also many recent developments on. It's related to what's called E-positivity, which then I worked also. So okay, so this is what comes to my mind. So and so then I just pass to a little won't have time to describe this this part of the theory, but there's an obvious yes. So let me just go back to the beginning. So so the question was whether RP2 can be immersed into R3, and as I said, that if we wanted to prove that it cannot, then this would be an efficient method, is to find a singularity class of whose homology or cohomology class in RP2 is non-trivial. Once we have it, then of course we know it cannot be immersed. That would be the topological abstraction. Well, if one calculates this abstraction, it's possible, it's easy, it is equal to 0, which is just as well, because as you know, there's a famous Boyce surface which says that you can immerse RP2 into R3. And so, okay, so that's that. But then the next question, you can you, how about embedding? So we already know it can be immersed, but how about embedding? Well, that is obviously not possible because this is a non-orientable surface. So what does it mean that there are immersion and no embeddings? It means that there are some double points. There are some points in the image of this map which have more than one inverses. So there must be double points. But the question is, so are there triple points? So we know they are double points. Are there triple points, for example? So that's now a valid question, which falls into enumerative theory of map singularities. And this is there are the famous multi-point formulas. So let me get to that. Get back here. And so here we are. So let me discuss a little bit at the end the multi-point formulas, which is describing some joint work with Gergely Birc again. So multi-point formulas, the idea is the following: same setup, mn, and we fix an integer. Now, in a certain sense, it's simpler for now, because we, instead of an algebra, we just fix an integer, and we look at the following locus mk, which is the locus of those points in the image. So I simplify the thing. There is some other setup as well, but let's just look at the image points in N, such that the inverse image, that there's at least k inverse images of this point. And this is a very simple definition. Again, there are lots of transversality problems, and here they are much more serious actually than in the other case, than the case of Tom polynomials. But still, it's a valid question to find the dual class for a generic, sufficiently generic map, whatever that means, of this multi-point class. So this is a very, very classical problem, which was before that, I'll just give you the answer for the two case. Well, the one case is obviously just f lower star of 1, so the push forward of 1. So now, since we are looking at all things on n, I'll have to kind of push forward things. And so the way this looks like is as follows. We take, so the famous double point formula, which goes back probably, I don't remember how, probably 80 years or something like that, is the following. So you just push forward the fundamental class of M into N, so just a class of the image of M. That's this, and you self-intersect it. And then what you do, you take CL of F, so the L Chern class, and I draw your attention that before the Tom polynomials is L plus 1th Chern class, L plus first ones. Here is the Lth Chern class. You take that of F, and which is of course the exact codimension, and then you push that forward. You subtract, and this is the answer for 2n. So it's this formula that we are trying to generalize. So so there's some work. It's about the same time scale as I was talking about before. There's the work of Herbert and Ronga, who the 70s for and Kleiman. Many of these works were giving some extra conditions. So you get a polynomial with some extra conditions imposed on the function f. So they would not be valid in general. Until the work of again, Martin, who set up a general, I would say, a general scheme of what the general answer should look like. And so then I will a little bit one of the problems, like in the previous case, I shoved it under the rug, but in a certain sense, I defined it at least precisely. I said the correct answer is an equivariant Poincare dual, which is a completely well-defined, honestly defined object in enumerative geometry. In this case, since this thing is delocalized somehow, so it's not so easy to understand what to even define this. So actually, just going backwards, for the definition of what this should be, there's a very recent, like this year, I think, work of Toru Omoto, who using algebraic Bourdisms gave an understanding of what this map is for a sufficiently big class of functions. So just what is precisely the meaning of this class is not so easy to define just starting from any function. So there is some technical details here which are, I think, still need to be worked out. And now going backwards in time, so as I said, Maxime was the one who really understood what the structure of this formula should look like. So let me say something about that. And I formed the conjecture. So there's this MK, the fundamental class, but as I said, this MK really what it is. Now we have an understanding. The most general understanding is this, that of the setup of Omoto, and the idea is the following. So this MK here is equal to the following thing. Let me just up. It was supposed to be a bar here of some sort. Okay, when am I? 3 minutes, right? Okay. So it looks like this. We look at all partitions of the number k. There's a combinatorial factor, just a number depending. It's basically a multinomial function, and then there's a product of f lor star of r I depending on j. So these are the j's are just indices from 1 to r, and so this product, if you like, goes until r. And so you have some class which you need to push forward, that this Rij, and the class Ri now is the same sort as the Tom polynomial. So this is just a class which is just a polynomial in these classes of the Chern classes of the F. So that's sort of the expected structure of the formula. So you can see here, for example, you see it's C0, it's one is C0, so C0, C0, it's this product pushed forward, and then you push forward CL of F. And so then, since we have this is always the same R, so now the question remains, what is R? And so this, in fact, R is simply equal to the ith Tom polynomial, but instead of L, there's this shift to L minus 1. So this is the conjecture of Riemannian. So altogether, so if you put these three things together, then what I'm saying is a conjecture about MK being equal to this, where Ri is equal to the Tom polynomial of I, Tom polynomial of the ADA AI singularity in codimension L minus 1. And so we have some recent work. Let me just see, where are we here? Okay. So, which is based, so my recent work with Gergely is a proof of this conjecture. But so what needs to work out is whether we can really make understand, sort of combine the setup of Omoto of the definition of this M. Otherwise, we need to restrict the function into more special ones. So there is some technical problem to put the whole for the whole proof of the conjecture, but we have a beautiful scheme for a set of functions, which is based on actually Kleiman's idea, who brought back this this topic to the center of of enumerative geometry. It's back in the 80s with Charles and Katz. And this is the interpretation of this in terms of the Hilbert scheme of points. So you look at the Hilbert scheme of points, which now I don't have time to explain this, but so in the Hilbert scheme of points, there's a particular called the geometric component, and this geometric component you can cut out this little piece where the schemes which go to zero by is sent to zero by f. You call it Hilbert scheme of f, and then this mk is just a push forward by f of this geometric subset. So this is our setup, and then there is a technique. There's a geometric sieve technology which recovers Kazan's form, and then there's certain residue vanishing, and finally the whole thing is reduced to an integral to the curvilinear locus, which is basically the same integral that we had in our original Tom polynomial formula, that for the Tom polynomial, and that basically recovers Riemanni's conjecture as well. As I said, this is to completely combine all three things. I think there is still some work to be done. We have it for some more special functions for now. Okay, maybe I'll just stop here. Thank you.
Thank you very much. Let us thank the speaker. Are there any questions?
Probably you commented something on that, but I didn't catch. When it's possible to define Tom Damon classes as elements of cobordism groups, or there is it's not possible only in cohomologies?
Yeah, so unfortunately now it's a dual thing, because now I don't hear anything. I mean, very little. Is there a microphone or something?
I asked whether it is possible to define Tom Damon classes as elements of cobordism groups, not of cohomologies. Or it's not.
In more extraordinary cohomology theories.
In bordisms,
Cobordisms. But so you mean complex cobordisms, you mean extraordinary cohomology theories, are just because so that to me it makes some sense, but yeah, so I don't know if they're invariant. I mean, that's quite more problem in general. Even for theory, it's not completely clear what means. You want that, I mean, these polynomials are universal, so you want to some invariants that push forward backs like they are for homological polynomials, and often these are not true, I think. But maybe I understood your question. But so as I said, we try to do this case here, and even there is some technical problems. Relatively speaking, we have this little locus I can show you. Like what we have. Okay, maybe it doesn't answer your question. Maybe it's still somewhat useful. Yes, so this might work with Riemanni. And so here what we have is that this is the wrong thing. Here, this one. Yeah. So in this work, so roughly what you need to do is to look at this setup, right? You look at this linear space with this subset, and then for cohomology we do some resolutions of this subset. But so these invariants that we look at, they are not invariant on these resolutions. So you need resolutions which have rational singularities. So I need rational singularities as singularities of this variety, and so there's various problems. So I'm not 100% sure how to go further from here. Maybe you meant something different to find them in bordisms, at least I'm not sure. Yeah, so through internet right now, I think that's all I can say as an answer. But maybe you can explain to me later what you want. Okay. Are there any other questions?
I have a question. Maybe you mentioned that, but yeah, I didn't yet. What is the status of AD? Is there an algorithm that allows to calculate the Tom polynomial for any given D?
Yeah. So this I know very well. So precisely the situation is as follows. So we have this. Where are we? Up. We are here. No. Here. Yeah, so this formula is valid, and so this QD is unknown. So at the beginning, one is very excited because this QD is much simpler to calculate than the Tom polynomial, because it's so where is no, that's not it. Sorry, up here. For example, even the Tom polynomial for d equals 3 was unknown, and Q3 is just 1. So that obviously says that this is this is great, and then Q4 was is also just linear, is easy to calculate, and then 5, 6 you can relatively easily calculate, maybe even 7. So it looks very good. I mean, eventually this becomes very just lots of terms. There is an algorithm, but it's not. Well, there's two issues. I mean, one is that already 7 I think less than 10,000 terms. So because this is a polynomial, what degree, I don't know, like 20 or something is a lot. So what does it mean? No moving answer is also a question. And then, but I would say that what it's difficult to measure what the answer would be. But what we can say is that we don't have an elegant, I mean, a non-generic algorithm. So this, at the moment, this algorithm is just a general algorithm for finding multiple degree of subtype. There are many ways of doing that, and we don't have a special algorithm for QD to calculate that. So in that sense, I mean, certainly still this structure that we describe here is a huge simplification, because QD is much smaller and it doesn't depend on N and M. So I mean, it's a much simpler thing. But this much simpler thing after d equals 8 becomes more difficult to calculate, and yeah, I mean, then it's a question whether there's maybe some other simpler ways of doing it. Another issue is that they might be, so this is Riemanni's work, for example, there might be ways, if you care about L equals 0, for example, so just for low L, then those small L's, they will only see a very small pieces of these things, that they might be easier to calculate than Q8. So for example, for d equals 8. So Riemanni had some, I think, calculated, for example, TH, the Tom point for L equals 0 and d equals 8. Now we don't even know what Q8 is. So in that sense, it's a somewhat of a perpendicular thing. And even if we knew what Q8 is, we would probably not be able to do this multiplication, because this computer-wise is just very difficult. So that's the status. I mean, at this point, it's a really important problem. Someone wanted to know what a certain coefficient of the Tom polynomial 10 is in codimension 3, because that was important. Then probably this would be a good project. For right now, this is where we are. I mean, yeah.
If there are no more questions, let us thank the speaker again. Okay, we have a 5 minutes break.
Thank you very much. Bye-bye.